Well, until the somebody Uberized our autonomous transportation, we need people like our next speaker, who developed from new material made of atmospheric carbon. His company specializes in making smoke-eating facade panels to combat the effect of low-level pollution in cities. Ladies and gentlemen, take a deep breath and welcome on stage Daniel Schwaag. If I said the name the right way, I'm doing my best. Daniel?
I've heard much worse. Thanks a lot.
Thank you. Thank you so much. Nice meeting you.
Nice
Here
meeting
you are, the clicker.
Thanks.
And here is the timer. Also,
All
that's
right. Okay. Yeah, hello everyone. It's unusual that we have two people talking about air pollution. We're normally the only ones at the Smart City Summit, so that's a really good sign. We're still probably the only architects that are talking about smart cities in this room. But let's get right to it, because the clock's going to start ticking. So this is the current state of building technology. This is building information modeling, and it considers the interior spaces of buildings to be technological spaces. So with controls for air conditioning, for air distribution, for climate control, for humidity data, etc. And we're increasingly extending this sort of control into the structural realm with the onset of IoT into construction. And we're getting ever more controls and tweaking and fine-tuning our environments using this technology for our interior spaces. But going beyond the level of the envelope of buildings, we're stuck with very turbulent conditions, such as weather or air pollution, noise, traffic. And the question is, when are we going to start to think of these environments in the same term as interior spaces? And so this is a very volatile environment. It's very volatile, it's very active. In a city like Beijing, air pollution is probably the single biggest impact on human behavior. It's an architectural condition, but the buildings that we see take no note of it. They don't respond to it. So talking about air pollution again, urban air pollution mostly consists of oxides of nitrogen, of volatile organic compounds, of ozone, of fine particulate matter. And in 2001, we discovered this technology, which is a light-activated technology based on superfine titanium dioxide. And it uses light to break down these pollutants quite successfully. And as a light-activated technology, it requires photons, it requires photon energy, it requires light. And it actually converts some of these pollutants into harmless substances, or all of them into harmless substances, and some even into useful substances, such as calcium nitrate. So it converts nitrous oxide into calcium nitrate, which is essentially a fertilizer. In biology, there's a link between surface area and light reception. Sunlight. Corals are a symbiotic relationship between polyps and algae, and together they benefit from the surface enlargement for better reception of light so they can photosynthesize, and for better exposure to nutrients so they can feed on the nutrients. So the question was, can this kind of surface enlargement benefit a photoactive technology? This is Prosolve. It's a facade module for the reduction of air pollution in cities. And what it does is it does exactly these things. It clusters the TiO2 technology in spaces in so-called pollution hotspots where we have the highest levels of pollution. And this is typically on facades because of their proximity to air pollution in the streets. Prosolve modules are made from thermoform plastic sheet. They're coated with a superfine titanium dioxide, which is photoactive. And the design of the modules is created in order to slow down air turbulence, air flow. So we have longer exposure times of target substances, and it maximizes exposure to UV light, which we need for the photocatalytic reaction. So in 2012, this was installed on a hospital in Mexico City. And talking about the surface enlargement, so here we have an installation of 2,500 square meters. Using surface enlargement, we achieve 5,000 square meters of active titanium dioxide surface. And it's been described as the smog-eating building, or possibly the world's largest urban air purifier. Another picture. And this geometry is called a quasi-crystal geometry. It allows us to achieve this complexity quite efficiently. It means that we only need 2 module types to create this complex-looking thing. So this is kind of a new technology that uses soft power, which is something new. We, to track back a little bit, we had a lot of conversations with a lot of smart home people, actually smart buildings people. And one of them, which is sort of this software paradigm, started talking to us about how buildings, or how companies like Schwaag, which is one of the largest window manufacturers, should actually be selling the service of transparency and not windows as a product. And this is essentially what we're doing. We're selling the ability of buildings to reduce pollution, and that's a big change. And sorry, to go back a bit. So what's happening on the surface is that we're actually, for the first time, sort of having a surface that is harnessing, that is precipitating things, useful things, as I mentioned before, turning nitrous oxides into calcium nitrates. Moving on to our second product, we have, over the last year, noticed this relationship between space missions and global warming. And this is that atmospheres can be seen as mediums, as growth mediums or a repository for materials. So in The Martian, the main actor is stranded on Mars, forgotten, and he has to basically precipitate and produce all the materials he needs from his Martian environments. So, and he's a botanist, and I think that's significant because he's actually using the thinking of photosynthesis to synthesize materials that he needs, such as rocket fuel, oxygen, hydrogen, etc. And of course, climate change, COP21, has reminded us that there is a lot of stuff in our atmosphere, that we're actually talking about a very rich atmosphere. There's a lot of stuff up there, stuff that we've put up there, and that we can harvest, that we can see as a resource, and that we need to harvest. There's a lot of technologies already that sort of deal with this idea of synthesizing from the atmosphere. This is an air bottle produced by Fontis, which synthesizes water from humidity in the air. And on the right, we have a plastic called air carbon from New Light, which essentially turns methane emissions into plastics, in this case, into plastic bags for laptops. And then going back, I'm really sorry that you have 2 air pollution people to sort of end on gloomy notes, but we have to talk about it, and this is that the case for carbon negative. So if you look at the results, the outcomes of COP21, there was a lot of enthusiasm about actually not only proclaiming that we can limit global warming to 2 degrees, but that we can even say 1.5 degrees. The thing that people are not so inclined to talk about, especially politicians, is all the mathematical scenarios to have any realistic chance of reaching this target requires that we think about methods of drawing CO2 out of the atmosphere. So in order to get this curve on the left, which is the red curve, which is what we're on right now, into something looking like the curve on the right, we have to take out of the air, according to the IPCC, the International Panel on Climate Change, 2 to 10 gigatons of CO2 out of the atmosphere, and that's a lot. But there is a very simple method, and it's very low-tech. It's called Biochar. It's the controlled pyrolysis of biomass, and it's essentially the baking of biomaterial, of biomass, into a stable form of carbon. And so all plant material that we have contains a lot of carbon from the atmosphere through photosynthesis. But the problem with plants is once they decompose, they release this CO2 back into the atmosphere. So what biochar does really well is to preserve this CO2, and we have the chance to sequester it thereby if we choose. We can make things out of this stuff that is stable. In this form, the CO2 is stable for tens of thousands of years, which is something we know, and this is really important. We know this empirically from archaeological data. So if you go to archaeological sites, you will always find sources of carbon or deposits of carbon that have actually resisted decomposition in the most sort of decomposing environments for tens of thousands of years. So the idea is if we use these carbon-based materials, you essentially get materials that the more we produce of them, the more we're drawing CO2 out of the atmosphere, the better for the environment. So these methods are sort of called, in the climate debates, they're referred to as climate capture and sequestration, or in this case, more specifically, direct air capture. You may have heard a lot lately about carbon neutral. This is what everybody's talking about. This is the scenario in the middle. But at the same time, for a long time to come, several decades more, we will practice the bad stuff on the left, which is the traditional carbon flux into the atmosphere to produce energy. So what we need is we need a process that actually draws the CO2 out of the atmosphere and makes use of it and sequesters it permanently. This is carbon negative. And again, carbon negative means the more we make of it, the better for the environment. I have to speed up a little bit. So we started making these tortillas a few years ago. It's a compound that contains 70% certified biochar. It's effectively 50% atmospheric carbon, which is why we've adopted the name made from air for this material. It's a carbon negative material. We're currently sequestering 1,000 kilograms of CO2 per ton of material. So why not think big? And we thought, can we have cities out of carbon? I'm going to have to speed up a little bit to show you the last pictures. This is prototypes of this facade module that we've made last summer. It's hexchar. It's a module that has that can be flipped to produce apparent randomness across the facade. It's robust. It's lightweight. It can be fireproofed. It's not an active material or a smart material as Prosolve is in that it's not active, but it's the beginning of a whole new class of materials that you see sprouting up at the moment, which completely inverts building methods. It changes the idea about construction products in the sense that the more we make of them, the more we design them, the more ubiquitous we make them, the better for the environment. It's an ecosystem of building materials. This is what we have to do. So 1,000 square meters of this material sequesters 10 tons of CO2. We're, as I said before, in contrast to Prosolve, where we had to deal with aesthetics to make the product grow, so to speak, faster. In this case, we have to scale up. So this is something we started to do, and we're currently in building certification and testing to release the product later this year as the first sort of carbon negative building product, really with a very impressive carbon negative balance. But as we say, it's sort of intended as a beginning. It's the beginning. We're starting with the facade and we're moving towards structural materials. So these are first applications of structural modules with which we can actually express double curvatures, which we can use for acoustic tuning. We can direct sound, we can deflect sound. We can even reduce the radar footprints of buildings using this technology close to airports. These are essentially all the applications, the array of applications you get in organic chemistry for materials from fossil sources. Thank you.
Amazing.
Thank you.
Thank you so much.